Chapter 1, lesson number 9 is on page 81, and this is estimating roots. We did a lot of estimating roots in class, but I know it's been a while, and so we need to do a refresher here for sure. Remember, when we estimate to the nearest integer, we have to find the two square roots or cubed roots on these ones that 28 is between, or the square root of 28 is between. Okay, so we're looking for two perfect squares. Remember, our perfect squares are 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, and I can keep going forever. These are called perfect squares. And I'm looking for the two perfect squares that are on either side of 28. So one that is smaller and one that is bigger. So if I look at 28, that's going to be between 25 and 36. I want two that are right next to each other. So 25 is 5 squared and 36 is 6 squared. So this is between the square root of 36, the square root of 25 and the square root of 36. Okay, so since it's between these two, it's going to be between the square root of 25 is 5 and the square root of 36 is 6. So my answer to this when I'm estimating will be between 5 and 6, because the square root of 25 is 5. That's a little bit too small because I want the square root of 28. And the square root of 36 is 6, but that one is a little too big. So somewhere between here, to figure out where it is, I would try to decide how far away 28 is from 25 and 36. So if I look here, it says 28 is 3 away from 25. So 28 is only 3 from 25, but it's 8 away from 36. So it's farther from 6 than it is from 5. It's closer to 5, which means my decimal would be less than 5. Okay, so 5.3 would be about what my answer would be here. And again, if we can use our calculator on this, then we can put this in the calculator. It does say to the nearest integer. So to the nearest integer would be about 5. When it wants an integer, I don't want a decimal. Okay, so it would be closer to 5 than 6, and 5 would be my final answer then. Okay, and then on number 2, it's the square root of 135. So I remember again that the square root of 121 is 11 and the square root of 144 is 12. So I know that my answer is somewhere between 11 and 12. This 135 is farther from 121 than it is from 144. So my decimal would be about 11.6. But again, we want an integer. So my final answer, I'm actually going to use the 12 because it's closer to 12 than it is to 11. So 12 would be the closest integer to the square root of 135. Here again, square root of 38.7 is between the square root of 36 and the square root of 49. 38.7 is only about 3 from 36, and it's about 10 from 49. So it's definitely closer to 6. If they wanted decimal, then I would put about 6.2. But the directions say to the nearest integer, and integers do not have decimals. So my answer here would be just 6. So I'm going to take off the decimal if it's asking me for the nearest integer. So 6, this is closest to 6. The square root of 51, this is the cubed root now. So 4, 5, and 6 have cubed root. And so I remember my cubed roots are 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, 4 times 4 times 4, etc., etc., etc. Okay, so these are my cubed roots. I'm sorry, my perfect cubes. 51 is between these two. So the cubed root of 27 is 3. The cubed root of 64 is 4. And this cubed root of 51 is closer to the cubed root of 64. So I'm going to round up and make it 4 for my closest integer. It's nearest to 4. If they want a decimal answer, then I would estimate that it's about 3.7. But if I want an integer, I have to put a whole, like an actual number. No decimals. Okay, cubed root of 200 is between the cubed root of 125 and the cubed root of 216. The cubed root of 125 is 5. Cubed root of 216 is 6. If you want to write them out on your paper so that you can look and see which one it's between, you're welcome to do that, because again, you have a calculator. So you can do 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, 4 times 4 times 4, and you can keep putting them in your calculator until you get a list of perfect squares or perfect cubes, whichever one you want. Okay, so this one is between cubed root of 125 and 216. Cubed root of 125 is 5. The cubed root of 216 is 6. And this 200 is much closer to 216 than it is to 125. It's very far from 125. So if they want a decimal, I would put about 5.8. But again, I want integers, so it's much closer to 6. So 6 is what I would write for my integer that the square or the cubed root of 200 is closest to. Cubed root of 95 is between the cubed root of 64 and 125, so it's between 4 and 5. 95 is closer to 125 by just a little bit. If I do 125 minus 95, I only get 20, and then this one would be just a little bit more than that, like 30. So I'm going to round it up to 5 as an integer, or 4.6 as a decimal. Okay, number 7 says, Humaid dropped a tennis ball from a height of 60 meters. The time in seconds it takes for the ball to fall 60 feet is 0.25 multiplied by the square root of 60. Find 3 sets of approximations for the amount of time it will take. Then, determine how long it will take for the ball to hit the ground. So this is a difficult question. We want to find approximations. So if we find the two numbers that square root of 60 is between, this would be 7 and 8. So it's about 8 if we want an integer value. And if I take 8 and multiply it, remember this is about 8, and multiply it by 0.25, I'm going to end up getting 2 seconds for my answer. So it takes the ball about 2 seconds to hit the ground. But this also wants 3 sets of approximations. And so this is a difficult question because I don't really know exactly what they're wanting by the 3 sets of approximations. I guess that I could say that this is about 7, about 8, about 9, and then multiply each of those by 0.25 to figure out which answer would be the best answer. But about 2 seconds is what I would put, because the square root of 60 is about 8, and multiplying by 0.25 I get about 2 seconds for it to hit the ground. Okay, the last one says the number of swings back and forth of a pendulum of length in inches each minute is 375 divided by the square root of L. About how many swings will a 40-inch pendulum make each minute? Okay, so I know that this says 40 inches, and I know that L is inches. So all I'm going to do is put this 40 where the L is. Okay, so 375 divided by the square root of 40, and I know that the square root of 40 is about 6. So if I do 375 divided by 6, I get about 60 swings. And that's all I have to do on this problem.